Okay, so to complete this first part on the motivation of our areas and how this hypothetical type of random generator would be a solution to almost all the problems that we have, I want to show you that if we had a construction of random generators with the properties that we described above, so a generator that is computable in polynomial time as exponential stretch, and for some even constant factor as this randomness property for all circuits of fixed polynomial size. So we saw that if we had that, then every randomized algorithm that runs in polynomial time can be made deterministic. That's the P equal BPP conjecture. Now let me show you a very simple consequence that also every application of the probabilistic method can be made constructive, provided that the property that you want to construct is checkable in polynomial time, and that you're not using something like the Lovász local lemma that give you positive but very small probability that a random object has the property. So you have a more typical application of the probabilistic method, where you show that not only a random object has your property that you desire with positive probability, but actually a fairly large constant probability. So let's say we are interested in constructing an object of a certain type. Let's say almost with no loss of generality, it's a bit string. Anything else can be encoded like this. So some element of 0, 1 to the n. That satisfies maybe I'll prefer to call this little n. That satisfies a property P. Let's say P is checkable in polynomial time, maybe as before in n cube time. And also the probability that P is true for a random x is maybe 20%. So we have an application of a probabilistic method in which we prove the existence of an object with a certain desirable property by showing that a random object has the property with reasonably high probability. And also, it is the case that the property you're interested in is efficiently checkable. Maybe that's the property of a graph being Ramanujan. So then, we can again set up the following two probabilistic experiment comparison. We can say, well, what happens if I pick x completely random? So that's the U-sub n is the uniform distribution over bit strings of length n. And then I pass it on to the algorithm that evaluates P. So this will tell me it's true, it's false. So 1 is true, 0 is false. And it will be 1 with probability at least 20%. So then let's look at the case in which we pick a bit string of length log n, maybe order of log n. We pass it to the generator the generator stretches it exponentially to length n, and then we give this to P. So here, in this instantiation of the generator, this will map something of length order of log n to something of length, let's say, n squared. And then we look only at the first n bits of the output. We'll see why we need to do this little processing. So I'm comparing what's happening if I evaluate the property at a truly random input, or evaluate the property at the first n bits of an appropriate instantiation of my generator. Well, the property is computable in time n squared. What did I say? N cube. So it's less than quadratic time in the parameter n squared for which the generator has been instantiated. So the computation of the property, we can think of it as being our statistical test. If here we had, say, one with probability less than 10%, our property would be an efficiently computable statistical test that is not fooled by the generator. So this would lead to a contradiction, which means that it has to be one with probability at least 10%. So if we have, essentially, if the probabilistic method proves that some string exists with this property, it's also proving that one of the possible outputs of the generator has this property. In fact, in this case, at least 10% of the outputs of the generator have the property. So then what do? We enumerate all possible outputs of the generator just by enumerating all possible inputs for the generator. So once more, we are enumerating bit strings of length order of log n, of which there are only 2 to the order of log n, which is polynomial in n. So we can enumerate all the polynomially many possible inputs for the generator. This will tell us what are all the polynomially many possible outputs for the generator. This comparison argument shows that among the outputs of the generator, there have to be many strings for which the property is true. So as the property is polynomial time checkable, so we will just enumerate all outputs of the generator until we find one for which the property is true. And that will be our constructive output. Like concretely, you could say, I know from I know that a random d-regular graph is with good probability very close to being Ramanujan. The eigenvalue calculation is doable in polynomial time. So I'll just run the generator, interpret the output as a d-regular graph. I'll keep doing it until I find one that is close to Ramanujan. That would be a construction that would fit into this framework. In fact, any probabilistic proof would fit just under those two assumptions, that the property you want to construct is checkable, and that your proof of existence is actually showing that the property is true with high probability. It doesn't have to be high, at least something like 20%, 10%. So then just to see how versatile this concept is. Now let's say that we have a randomized algorithm like the Jerome Sinclair-Vigot algorithm for approximating the permanent of a matrix. So that's a randomized approximation algorithm. So it's an algorithm that will take an input a matrix, take an input some randomness, and then will output a number that will be an approximation to the permanent of the matrix, with high probability. Usually permanents are huge numbers. So this will have the property that with probability, say, at least 90%, the output is the correct value up to some small multiplicative error. You can choose any epsilon you want that will go into the running time. Now we would like to get the same arbitrarily good approximation deterministically in polynomial time. So by analogy to what we have been doing so far, we will want to look at the experiment of picking a random string, and now we'll have only log n bits. Use that as an input to the generator, and then the generator is instantiated so that its output matches the amount of randomness in it by the algorithm. The kind of tests for which it works matches the running time of the algorithm. But now it's not immediately clear how we apply the reasoning that we have done so far, so now intuitively we want to take this algorithm as our statistical test, and then say that since things work here, they also have to work here. In particular, I want to argue that there is probably at least 80% that here we get an answer that is 1 plus or minus epsilon of the correct permanent. So now the way of turning the algorithm into a statistical test would be to add a Boolean computation that says whether the output of the algorithm is within 1 plus minus epsilon of the value of the permanent for that matrix. And do it the same for the truly random case as well. Yes, that's where it gets tricky. Right? So we want this to be our statistical test, but for this to be a statistical test, it needs to be something that is efficiently computable. But so part of our definition is a computation of what we are trying to do. So it seems we are completely chasing our tail. But this is another place where it's important that our model of what is a valid test is an arbitrary Boolean circuit. Again, what is a good way of thinking about a Boolean circuit of a certain size? It's an arbitrary algorithm that is a running time up to the size of the circuit, but also whose description is an arbitrary description, like as many lines of code as you want, up to the size of the circuit. So this model of thinking of algorithm running in time at most t with at most t lines of code is a kind of if and only if characterization of circuits of size up to t within polynomial factors. So that means that, okay, what does it mean? So now suppose that here, this works with probability less than 80%. And I want to now contradict the goodness of the generator. To contradict the goodness of the generator, I have to come up with a Boolean circuit that implements this statistical test. Because if such a circuit of size comparable to the running time of the algorithm exists, it would be a contradiction to the definition of the test. But notice that I need to show that the circuit exists. I don't need to explicitly construct it. Because the definition of the generator says, for every statistical test computable by a circuit, it needs to be fooled. So the negation of that is that there exists a Boolean circuit that is not fooled. There is nothing in the statement that says that we need to know how to construct it. Just need to show it exists. This whole thing is only in our head, in the analysis of the algorithm. So how do we argue that such a thing exists? Well, if this happens, there is some matrix M for which this happens. We will stick M into our description. Now M is fixed, so it has some value of the permanent. We stick that value of the permanent into our description. So now this whole thing is a small circuit. It's a small circuit that we don't know how to construct, but it's a small circuit that most definitely exists, and whose size is comparable to the running time of the algorithm. So now the circuit exists, it's small, it's contradicting the goodness of the algorithm, so actually it doesn't exist. So we reached the contradiction. And the contradiction was started by this assumption. So this assumption needs to be false. It's actually that with probability more than 80%, the output has the correct approximation. So now that we have that, what do? We again enumerate the polynomially many possible inputs for the generator, and we run the algorithm using that randomness. So then we will get polynomially many runs of the algorithm that will give us polynomially many approximations of the permanent. What do we know about those approximations? That 80% of them are within 1 plus or minus epsilon of the correct value. So then how do we aggregate all these polynomially many numbers to get just one approximation that is guaranteed to be 1 plus minus epsilon? Huh?
A median?
We take the median, because since 80% of the values are correct, the median needs to be in that range. So that's what we do. We take the algorithm, run it over all possible outputs of the generator, get lots of outputs, then take the median of those outputs.
Is there a relaxation of the notion of pseudo-randomness that will rule out this counterexample? Like, under which such a construction is not possible. We kind of cheated here, right? Because the test, we cannot come up with the test, we just know it exists.
Well, so that's good. That's a power of the construction. It says the construction works for every test, whether you, all of them, right? So you don't need them to have any kind of small description. And we believe that generators like this do exist. And they do exist under reasonable assumptions.
But you needed to know M.
No. I need to know M to construct this circuit. But if I know that M exists, I know this circuit exists.
Right.
So M and this box exist only in the analysis. They don't exist in the algorithm. The algorithm just says, I have an input M, I run the algorithm over all the possible outputs of the generator, I take the median. That's the end of the algorithm. Then in the analysis of the algorithm, I say, suppose there was some matrix where this doesn't work. Well, that matrix has some value of the permanent. That matrix and that value of the permanent imply the existence of an algorithm, of a circuit like this. This circuit contradicts the randomness of the generator, and nothing like this can exist. Yeah, Ras.
This is a total digression, but say we had a notion of pseudo-randomness versus probabilistic polynomial time tests rather than circuits. Well, we would still need to know how many, it would still have to fail for a large number of m's, but we could use the JSV algorithm itself to probabilistically find with high probability, find the value of the actual permanent and test that we're close to that. And so this method would still work. For most m's. So you could weaken it and still have this result be true.
So the algorithm just gives the correct answer, or rather, approximately correct answer 80% of the time, right? With probability 80%.
No, there are always two phases. Like first, I start from an algorithm that uses as much randomness as it wants, and it has correctness probability 90%.
Right.
Then I say I can get an algorithm that uses only log n bits of randomness. It has correctness probability 80%.
Yeah.
Then I say I get an algorithm that uses zero randomness, and hence has no error.
In the next jump, you said that we'll run this 80% algorithm many times and take.
No, not many times. On all possible choices of randomness. So the randomness is not selected randomly. The randomness is enumerated over all possible choices. So everything is deterministic.
So look, maybe just a philosophical thing, and if it takes too long, so practitioners, putting like my practical ahead for a second, so somebody like Daniel Bernstein, he would like to write papers bashing the fact that our security notions are for non-uniform attackers, because essentially it's good that we achieve it, but he says it's kind of an overkill because we protect about unrealistic attacks that know some values and so on. Like for example, according to this definition, like AES has security at most 2 to the minus 64 instead of 2 to the minus 8 and so on.
Yeah, without getting it.
But essentially, just to point, so what's your view? Is it, I understand it's nice definitionally, but do we, do you still stand that maybe we should, continue this non-uniform model of security, because it leads to a lot of confusion and this kind of things that intuitively seems like cheating. What's your view? Is it something that...
Okay, the way I view it is to say, like in almost all complexity theory, kind of proofs come first and definitions come later. Like, so here, there is this argument that you want to use a generator to reduce randomness to the point that you don't even need it anymore. You can just enumerate it. Okay. So what definition of pseudo-randomness makes such an argument possible? Non-uniform definition. And you could say, well, but as Russell said, what if I only had the generator that I am trusting to be secure against uniform attacks? Then in that case, there is an argument to be made that how could this possibly fail? It fails when you get a matrix for which this doesn't work. But where is that matrix coming from? Somebody is able to come up with those matrices because they gave those matrices to us. So there is a way to construct matrices for which it doesn't work. And so kind of concretely, you could say that if the generator is secure uniformly, this at least works well on average for every sampleable distribution. If it didn't, you would know how to come up with it. And then you could say, really, when things work well on average under any sampleable distribution, as far as I'm concerned, this is as good as working well in the worst case. Because nobody will be able, maybe my algorithm is wrong, but nobody is able to come up with instances where it's wrong. Which is sort of roughly, although everything is going backwards instead of forward, what's going on in crypto.
For this thing, it's okay. So you're saying, like Russell said, for this thing it's actually okay. So
I'm saying this is a proof. Yeah. Do with it what you want. Right? You take some assumptions, it will give you some conclusions. If you really like this proof to tell you under what conditions you get a worst case algorithm that randomizes, the correct notion of security for the generator is non-uniform. If you are attached to the uniform definition of security, this proof will give you a good on average de-randomization. So that's how I would philosophize about this. Yeah.
The other thing is that if you want worst case,
if you want the worst case de-randomization, the case pseudo-randomness, it implies circuit complexity, and it implies a pseudo-random generator that is non-uniformly secure. So there is no shortcut. Yeah, good point. Okay, so I'm about to kind of turn a page from kind of describing motivations and definitions, and then now I want to start constructing generators with various properties. So if actually I'm not too concerned about time because I didn't plan yet for lecture number 4, assuming that I would go much slower than planned. So I think we are fine. So if there are more questions, I'm happy to answer them. Otherwise, we'll start talking about constructions.
Can we save some more
Yes.
by, rather than enumerating all O of log n random bits there, just trying to repeat the same trick? Say, I'll randomly pick some such string and use it for the test.
Yeah, so you could say, can you bootstrap this and get to log n? But actually, maybe in the uniform setting, but in the non-uniform setting, there is a bottleneck that the seed needs to be at least log of the complexity of the algorithms for which you want it to work. So this cannot be bootstrapped any further in this setup in which you want worst case complexity. Actually, no, I'm sorry. That's even in the even in the uniform case. You just cannot be secure. Some of that depends really on fine points about the definitions. But in general, one way to break a generator is if you get some string to be able to figure out if it's a possible output of the generator or not. Because if you can do that, you can certainly break completely the generator. Now, one way you can check if something is a possible output of the generator is to enumerate all possible inputs and then figure this out. So if the running time that you allow the test is less than exponential in the seed, that can be a problem. Although not necessarily because there are some loopholes, but that's one reason why there is this logarithmic barrier.
The first part of finding a generator would be to find a representative polynomial size sample of the 2 to the power n string, right?
But if you pick at random polynomially many strings,
But like if from the 2 to the power n bit strings, I take a polynomial size string, polynomial number of n bit strings, which satisfy the property that it's always like 80% of the time it has 80% correct and 20% wrong.
that's exactly the same problem, pretty much.
It won't be exactly the same because like it might not be convertible to a log n bit thing in polynomial. Like G has to run in polynomial time too.
Yeah, but if you can construct such a polynomial size set in polynomial time, you can make it into a G by saying what's string number I in lexicographic order. Okay, so let me. So that's. So let's see the simplest test that we can think of. Suppose we want to come up with a length expanding generator where the only statistical properties that we allow are to look at one of the bits of the output. So we want the generator to be such that the marginal distribution on each output bit is unbiased. So what would be a very simple way of achieving that? Yeah, exactly. So this is a one bit input, you just repeat it n times. So with probability half, you get 0, 0, 0. Probability half, you get 1, 1, 1. Now that's really trivial. Although there's a bit of a story to this, that some of the initial idea, the first paper that came out about talking about randomized algorithms, approximation algorithms, was by David Johnson in 1974. He talked about a few optimization problems and how you could get some kind of approximation for them. And one of them was max-sat. It's a problem where you have a conjunctive normal form expression, end of ORs. You want to satisfy as many of the ORs as possible. And his observation was, if you pick Boolean values at random, half, at least, of them will be true. And then he gave a way to constructively satisfy at least half of those clauses. Then, but in a way that is very sequential. Then later people were wondering, can we do that in parallel? And then they say, well, we can come up with a distribution where this is true, but with some kind of pseudo-random generator, evaluate it in parallel, and so on. It was an actual paper doing that. And then Michel Geymans observed that your generator could just be this, because for the argument to work, you just need the marginal of each bit to be unbiased. And that's very parallelizable. So. All right, so let's see something that actually is interesting. So let's say we want to, again, come up with some big expansion generator such that the marginals of every pair of output bits is unbiased. So they're pairwise independent. The bits of the output are pairwise independent. So here is a simple construction. It only uses the fact that two linear equations in n variables have a solution space of dimension n minus 2. So we will assume we can get n to be 2 to the t minus 1. So we will get an exponentially big stretch. T will be log n, or log of n plus 1. And it works as follows. Let's say we have some input z. So the output will be the, and we're going to think of z as being a dimension t vector in a field of size 2. So this will just be the inner products of this vector with all the other vectors in the space. All the non-zero vectors in that space. So these are inner products in f2 to the t, which means that all operations are modulo 2. Actually, this works also in other fields. So first of all, let's see. Every bit is unbiased. Why is it unbiased? It's the inner product of vector z by this random vector z by a fixed vector a. So I'm not sure if I'm belaboring the obvious, but suppose we look at the condition under which for how many z's this inner product is going to be 0? Well, that's one linear equation in Z. So that's the space of Z's for which this happens has codimension n-1. So this is a field of size 2. So it has there are 2 to the n-1 cases where this happens. There are 2 to the n cases in total. So this happens with probability half. And same for the other condition. So each bit is unbiased. Now I want to argue that any 2 bits are also, the marginal distributions are taking all the 4 possible values with probability 1/4. All values occur equally likely. Well, let's look at any 2 bits of the output. What are the chances that for 2 different bits of the output, A and A prime, say they are both 0? Well, those are 2 linearly independent equations in Z. So the space of solutions has codimension 2. And so this happens a quarter of the time. Now, no matter what other right-hand side you write, this will still be 2 linearly independent equations over the Z's. So the space of solutions will be in a affine space of codimension 2. And so this happens a quarter of the time. Quarter being the size of the field squared. So maybe a tiny example will give some idea of what goes on. If we have, say, 3 input bits, we're going to get 7 possible output bits, which will be all the F2 linear combinations of the 3 input bits, except the 0, 1. So our 7 output bits will be Z1, Z2, Z3, Z1 plus Z2, Z1 plus Z3, Z2 plus Z3, Z1 plus Z2 plus Z3. So our 3 input bits are mapped into these 7 output bits. These pluses are F2 pluses, so they are XORs of bits. And now you can take any 2 of them and then see that as expressions, they are linearly independent. So when evaluated for a random Z, they will be stochastically independent. And in fact, that's a reason why linear algebra is often useful in our setups, that when you have expressions of some randomly chosen objects in a finite field, and those expressions are linearly independent, the evaluation over random vectors will be stochastically independent. So it's very easy to reason about linear algebra, so that it gives these kind of consequences. Any questions about this construction? And this is also best possible. You can argue that with less than roughly log n bits, you cannot get n pairwise independent bits.
It doesn't work for triples.
It doesn't work for 3-wise independence. Yes, but we'll fix that. That's a very good point. You can find, for example, if you look at Z1, Z2, and Z1 plus Z2, those are not mutually independent. In fact, one is determined by the other. And in fact, the sub-collections of output bits that are not stochastically independent are precisely the sub-collection of expressions that are not linearly independent. So the two map perfectly to each other.
You can still get exponentially many that are each triple are linearly independent.
We'll get there. We'll get there. 3-wise will get there. I think first I wanted to show you something else. Before doing that, I want to do something that has a lot of applications in computer science, where instead of coming up with a collection of bits that are pairwise independent, I want to come up with a collection of values that are pairwise independent. Or another way of thinking about it, I want to come up with a pseudo-random function that maps maybe n bits into m bits, so that the evaluation of these pseudo-random functions are pairwise independent. So maybe that's a conceptual leap that, if you haven't seen it, might be slightly confusing. So I want to do the following. I want to start with t random bits. And then I want to come up with some function h So previously, I was coming up with a string of n bits, which I could have been thought of as mapping a domain of size n into 1 bit. And now, this is the same as a string in 0, 1 to n. But now, instead of coming up with a collection of pairwise independent bits, I want to come up with a function such that for every 2 inputs x and y, h of x and h of y, their marginals, are uniformly distributed. In this case, not among bits, but among bigger domains, and they are independent. So is the analogy clear? This is a bit like thinking about a string that has 2 to the n characters, and each character could have 2 to the m values. But it's much more natural to think of it as just a function that maps domain elements to codomain elements. And what we want this random function to be such that is that if you fix any 2 inputs and then you pick the function at random, the corresponding outputs will be independent and uniform. Is the definition of the problem clear now? Okay, so it takes more to describe the problem to describe the solution. So let's say first, and then it's easy to reduce to this case. Let's say that n and m are the same. We're going to work in the field okay, we're going to switch back and forth between so we're going to work with a field of size 2 to the n this time, but we will also think of the field elements as being n-bit strings that form a group with respect to addition. The addition in this field is the same as the addition in this group. We are making it sound too complicated. I'm just saying in this field, elements are n-bit strings. Addition is bitwise XOR. Multiplication is something complicated. I mean, you have to interpret the bits as coefficients of a polynomial, and then multiplication is polynomial multiplication modulo an irreducible polynomial. Okay, good. So we're going to work on this field, and So the input of the generator will be two field elements. So that means that T will be 2 times n. And the corresponding function is just ax plus b. Yeah, once more, so I want to construct a function that maps n bits to n bits so that evaluation at any 2 points are independent. So how do I define a function that maps n bits to n bits? I'll think of n-bit strings as being elements of a field of size 2 to the n. The input for the generator will be 2 random field elements. And then the output of the generator will be this function h, that on an input x outputs ax plus b. Here, this product and this sum are in the field of size 2 to the n. Now again, our generator has exponential stretch, because if we think about how big is this function that we are constructing, it has 2 to the n inputs, and each output is n bits. So the complete description of the function is n times 2 to the n bits. The input is only 2 times n bits. So we have even a little bit more than exponential stretch. Okay, now we need to argue pairwise independence. Maybe let's argue first that, so what we need to argue is that for every x different from y, over the randomness of a and b, ax plus b and ay plus b are uniform and independent. So now maybe this is a bit confusing, because now that we're going to use linear algebra to make this argument, we need to think of x and y as being constant, and a and b as being variables. So that's unfortunate, but we can all get over it. So okay, so we want to argue these are uniform and independent. So that means that there are 2 to the n times 2 to the n possible values that this pair of outputs can take. And we need to argue that they all have the same probability, which will have to be 1 divided by 2 to the n times 2 to the n. So what is the probability that for some fixed values v and w, ax plus b is v and ay plus v plus b is w?
This is probability over picking a and b.
Yes, probability over probability over a and b. Everything else is constant. We need to argue for every 2 fixed inputs x and y, for every 2 possible outputs v and w, the probability that those inputs gives us those outputs are always the same. All right, well, what are they? But this probability will depend on how many solutions A, B there are for these linear equations. How many solutions there are? These are two linearly independent equations because x and y are different over two variables, such that they can have only one solution. So there's only one choice for A and B for which this happens. So it's true that it's always the same probability, because it will always be 1 divided by the number of A's and B's that you have, which is 2 to the n times 2 to the n.
But you didn't need A to be random for that.
No, I totally need A to be random, because otherwise, if...
You only needed B to be random.
No, if A is fixed, the difference between those two values will always be A times x minus y. So it will depend on x and y. Imagine A is fixed, and now you're looking at those two values, ax plus b and ay plus b. Those are not independent over the choice of b, because their difference is fixed. Also, it's just a matter of counting that for those to be independent, they need to take 2 to the n times 2 to the n possible values. And if your sample space doesn't have size 2 to the n times 2 to the n, that's just numerically impossible. Okay, so this tells us that we can generate a function mapping n bits to n bits that is pairwise independent. And the input for the generator is 2 times n bits. So now let's look at the case in which we're interested in constructing such functions, but where the length of the input and the length of the output are different. So I will not give the most optimized construction, but it's sort of good within a factor of 2.
And you still require the uniformity of the distribution, because here you want independence.
Oh no, they were also uniform, because what I'm arguing is that for every...
No, I see that you get the uniformity, but when you write the new requirement now, you also...
when I say pairwise independent, I mean, this is used as a kind of technical term to mean that the outputs are pairwise independent and uniformly distributed. Yeah, thanks, good question. Okay. So now I want to generalize this construction to the case in which the input length and the output length are not the same. And so start applying this philosophy. I want to use this construction and change it so that I achieve this other goal. So how can I do that? Suppose that I'm interested in a case in which m is smaller than n. So I can use the construction that goes from n to n, and then ignore some of the bits of the output. That's because if the entire output is uniform and pairwise independent, if I ignore part of it, what remains is still uniform and pairwise independent. Okay? So if I want m less than n, I'm good. Now suppose I want m to be bigger than n. So what I will do in this case will be to apply my balanced construction with the parameter m. So I will get a function that maps m bits to m bits. So now I have a function that takes a bigger input than the one that I provided. So I will compensate for that by adding to my input m minus n zeros at the beginning. So, so now the types match, and if all the original 2 to the m inputs produce pairwise independent outputs, the subset that I'm using will still be pairwise independent. And I'm not touching the outputs this time. So the outputs will be uniform and pairwise independent. So, so that means that what I'm doing is to use 2 times max mn bits. So this also gives an alternative construction to the case in which I'm interested in a string of bits, which corresponds to the case m equal 1. So then I get 2 to the n pairwise independent bits using 2 times n bits as a seed, which is a little bit worse than what I had before when it was 1 times n. So that's why this is not always optimal. But within a constant factor it is. In fact, you can prove that you need at least max mn to get this construction. So it's within a factor of 2 of optimum. So if instead of using a field of size power of 2, you use a field of prime size, you get practical constructions here. The kind that are actually used to hash values in data structures. Okay, maybe I'll leave you on a cliffhanger. What we'll do next time will be the same, but instead of wanting to come up with a function where the values of every 2 evaluations of the functions are independent, or come up with a string where every 2 entries are independent, we will come up with something where for every fixed k, it could be 3, 25, 42, you have the property that every k bits of the string you produce are mutually independent. Or in the case of the function, the value of the function at any k evaluation points is mutually independent. Okay, I think I'll stop here. Thanks.